Welcome to The Explainer. Today, we're going to tackle one of the most powerful ideas that's totally reshaping modern AI, contrastive learning. It's a method that teaches machines to understand the world in a way that, is surprisingly human. So here's the game plan. We'll kick things off with the huge problem that contrastive learning was basically invented to solve. Then we'll dive into its core idea, learning by comparing. After that, we'll look at the key building blocks, the whole pipeline, and then explore its real-world impact and why it's really a brand new way of thinking about AI.
All right, first things first. To really get why contrastive learning is such a big deal, we need to understand the fundamental challenge it was designed to overcome in the first place.
So let me ask you this. What do you think AI's biggest weakness? I mean, you could probably think of a few things, right? But one of the most significant is its crazy, insatiable appetite for a very specific kind of food. And that food is labeled data. For years, as you see on the left, traditional AI has depended on this slow, expensive assembly line where humans have to manually label every single thing. This is a cat, this is a car. It's a massive bottleneck. But contrastive learning, over on the right, completely flips the script. It figures out patterns and relationships all on its own, learning directly from raw, unlabeled data. Okay, so how on earth does it do that? Well, this brings us to the core idea, which is actually based on a concept that you and I use every single day, learning by comparison. At its heart, contrastive learning is what we call a self-supervised method. That just means the model learns without needing labels from humans. Its entire goal is to make sense of the world by asking one simple question over and over and over. Are these two things similar or are they different? It's not about memorizing answers, it's about learning the relationships that are already hidden inside the data. And the way it brings order to this messy, complex world is guided by one just beautifully simple principle. Okay, this slide right here, this is the entire philosophy of contrastive learning in a nutshell. The model is trained to do just two things. One, take similar items, like two different pictures of the same cat, and pull their representations closer together. And two, at the exact same time, it takes dissimilar items, say a cat and a bicycle, and pushes them as far apart as possible. That's it. That's the fundamental rule that drives everything else. So how does the model actually follow that simple rule? Well, it relies on three key building blocks, something called pairs, a concept known as an embedding space, and a really clever technique called data augmentation. First up, the model learns from pairs. A positive pair is just two different views of the same thing. So think of a photo of a cat and then that same photo cropped or maybe rotated. That's a positive pair. A negative pair is even simpler. It's just two different things, like a picture of a cat and a picture of a car. So it's pushing and pulling these pairs. But where? It all happens in something called an embedding space. The best way to think about this is like a smart, multidimensional map. The model's whole job is to learn how to place every piece of data on this map so that similar things, like all the pictures of cats, end up clustering together, and really different things, like dogs and cars, end up far, far away from each other. But wait, how do we create those positive pairs automatically? We can't do it by hand. This is where a clever trick called data augmentation comes in. We take a single image and just create tons of variations of it. By showing the model all these different versions and telling it, hey, these are all the same thing, we force it to ignore the superficial stuff, like the color or the angle, and learn the essential unchanging features. It learns the very essence of catness. Okay, so we've got the building blocks. Now let's put them all together into the full contrastive learning pipeline and see how this thing actually works step by step. So this whole pipeline has 4 key steps. First, data augmentation creates those different views of our input. Second, the encoder, which is really the brain of the whole operation, it looks at these views and plots them as coordinates on our smart map. Third, a little helper called the projection head, fine-tunes those coordinates to make them easier to compare. And finally, the contrastive loss function acts like a teacher. It measures the distances on the map and tells the encoder exactly how to adjust its strategy to pull the similar things closer and push the different things further away. You can think of that loss function as the mathematical engine that's driving this whole process. Early versions used something called triplet loss, but a lot of modern frameworks use more efficient methods like InfoNCE, which is really good at comparing one positive example against a whole bunch of negative ones all at the same time. Okay, enough theory. Let's get to the good stuff. Why does any of this matter? What is this powerful learning technique actually unlocked out there in the real world? Well, for one, it has led to much smarter search engines. Because the model understands the meaning behind an image, not just the pixels, you could search for fast red sports car and get back pictures of Ferraris and Lamborghinis, even if those specific words aren't anywhere in the description. It understands the concept, not just the keywords. It also powers the recommendation systems that we use every single day. By understanding the deep similarities between items, it can suggest a movie with a similar vibe, not just the same actors, or a song with a similar feel, not just the same genre. The recommendations get so much more nuanced and honestly, just more useful. And this is a big one. It plays a huge role in perception systems for autonomous driving. A self-driving car needs an incredibly robust understanding of the visual world around it, and contrastive learning helps it build that understanding from just massive amounts of unlabeled driving data. And the impact here is just massive. It's not limited to just one domain. We see it in computer vision for things like face recognition and analyzing medical images, but also in natural language processing, where it's used to understand the subtle similarities between sentences and entire documents. So let's zoom out one last time, because this isn't just another clever technique. It really represents a fundamental shift in how we think about teaching machines. Look, on the left, you have traditional supervised learning. It's kind of like training a specialist for one single job, and that's it. Contrastive learning on the right is totally different. It's not learning one specific task, it's learning a rich, general-purpose map of the data. And once you have that amazing map, you can use it as a starting point to solve so many different tasks way more quickly and efficiently with a lot less data. This is exactly why you hear experts say it represents a paradigm shift. By focusing on similarity instead of explicit labels, it unlocks the incredible potential of the massive amounts of unlabeled data that are all around us, everything from the entire internet to vast scientific data sets. And that brings us to a final, pretty powerful question. By learning through comparison and contrast, contrastive learning is really mirroring how we humans make sense of the world. So, what becomes possible when our most powerful AI begins to learn less like a machine that needs constant instructions and a little bit more like us?